So now, following the first couple of rules of differentiation for the sums, subtractions, and power, we're going to add the rule for the product of function and the rule for quotient of functions. So first, we have the rule for the product of functions. And you could think that it was going to be the product of derivatives, but it turns out it's not. When we have the derivative of the product of two functions, this is going to be equals to the derivative of the first function by the second function without taking any derivatives, and plus the first function without derivatives times the derivative of the second function. Now, that's for the product rule. So let's do a quick example of this. Let's assume that our function h of x is now sine of x times e to the x. So we can say now this is going to be our function f, and this is going to be our function g. So this means that this is a product of two functions, f times g. So if we follow the formula of the product, we're going to have this. And what this means is that we get to find out what's the derivative of this function f and the derivative of the function y, and we can plug them in the formula. So we can actually do that on the side. F prime of x is the derivative of sine of x, which is going to be cosine of x, and the derivative of g prime of g is going to be g prime of x, and it's just e to the x. Now, that means that the derivative of the function h, which is the product, is going to be cosine of x times e to the x plus sine of x e to the x. Okay. Now, the quotient rule is very similar to the product rule, but some things are going to change. Now, if we take the derivative of the quotient f over g, we're going to have the derivative of the function f times g minus the function f times the derivative of g. Notice that we don't have a plus here instead, but we have a minus. And now, after we're done with this part, we divide by the function g squared. So again, let's take a look to a quick example. Now we define the function h of x to be the quotient of f over g, where those functions are going to be the polynomial x squared plus 2x minus 1, and g of x is going to be the log of x. Now, according to the formula, we have h prime of x is f prime times g minus f times g prime divided by g squared. So that means f prime is going to be the derivative of that polynomial. So it's going to be 2x plus 2. And the derivative of g is going to be the derivative of log, which is 1 over x. Okay. Now I'm introducing some derivatives right here, like the derivative of the log. Notice that using that to replace in the formula, we get 2x plus 2 times log of x minus f, which is a polynomial. And so I'm going to have to move this below, so I'm going to have a space here. So 2x plus 2 log of x minus x squared plus 2x minus 1 times 1 over x, and everything divided over log of x squared. Okay. So notice this can be very involved, and the fractions that you're going to get are sometimes not very pretty, and a lot of the work that has to be done here has to do with simplifying. Now, let's check some more examples for the product rule and the quotient rule. So let's check what is the derivative of e to the x cubed, the derivative for 5x minus 2 over square root of x, and the derivative of x squared plus divided 2x plus 3, and what happened if we actually do higher order derivatives. Okay. So let's put some of this function in here. So first, derivative of e to the x cubed. Let's go for this one first. Notice that this is a product rule. We can classify this as f, this is g, and so we can write e to the x, which is f prime, times 3 times x cubed, right? Since I don't need to do any derivative for g here, plus e to the x again, because that's f, times g prime, which is 3x squared. Okay, so that will be the first one. Now the second example is a quotient rule. Again, if we want to play with powers, it's going to be much more easier. So I can transform the square root as x to the 1/2. Okay, and now apply the quotient rule. So notice I'm going to go for the quotient rule directly. I'm going to say, okay, so the derivative of 5x minus 2 prime, and this prime means the derivative, times x to the 1/2 minus 5x minus 2 times x to the 1/2 in prime divided by x to the 1/2 square. Okay. And so now I can actually go and work with whatever these primes are. So the derivative of 5x minus 2 is going to be 5, since the only thing here is this 5x, and this is going to produce a 0. So I get 5x to the 1/2 minus 5x minus 2. And the derivative of a square root, you guys already seen that from our previous video. That's 1/2 x to the minus 1/2. Now the bottom below is a square root square, so we're gonna lose the square root. We're gonna get x. So we can actually say that we're done at this point. And if only finding derivative, we can stop at this very moment. Or we can just simplify a little bit by multiplying some of the terms. So in this case, this is going to be 5x. And if I'm going to multiply by this one, I get 5/2. And I get x. 1 minus 1/2 is going to be 1/2. And now this minus and this minus is a plus. So plus. And this 2 with 1/2 goes away. And so we get x to the minus 1/2 over x. Notice that you can simplify a little bit more these two terms. And you're going to get 5/2 x to the 1/2 plus x to the minus 1/2 over x. And this will be the more reduced, then we can have this expression. Now let's go for another example, the derivative of x squared over 2x plus 3. And here again, we can use the quotient rule. So remember, derivative of the first function times the second one minus the first function times the derivative of the second, the minus in the middle, and then we get 2x plus 3 squared. Remember that this is a prime representing derivatives. And so now this is the derivative of x squared is 2x times 2x plus 3 minus x squared times the derivative of this, which is 2, over 2x plus 3 squared. Now at this point, again, we can simplify. This is 4x squared plus 6x minus 2x squared over 2x plus 3 squared. And so we get 2x squared plus 6x over 2x plus 3 squared. And that's the end result for this quotient rule. Now, this is just a recall of higher order derivatives. We're not really using any specific product rules in here. So let me just transform this into example for a product rule, for a quotient rule. So let's consider f of x equals 2x cubed plus e to the x, and let's actually divide this by x. Okay, so if we do that, then now this becomes a quotient rule, and f prime of x is going to be the derivative of this times the second one without taking the derivatives, the function, the original function f, times the derivative of x, which is 1, divided by x squared. And so that's the first derivative. The derivative of this will be 6x squared plus e to the x times x minus 2x cubed minus e to the x, okay, and divided by x squared. So I can transform this a little bit more. This is going to be 6x cubed plus x e to the x minus e to the x minus 2x squared over x squared. Okay. Of course, you can take higher order derivatives for function like this. You can still take the derivative of this function, and that's going to be a very long derivative. So let's just give you a small idea of how that will be. So the derivative of the top function will be the derivative of this, of course, times x squared minus this without taking any derivatives times 2x over now x to the 4, which is the square root of this. And of course, then we get to do what is the derivative of this function, and that itself is going to have a product rule inside. So you got to be very careful when going forward. But for now, I'm just going to leave it here on the general idea. Now, with this type of functions, we can still do equation of tangent line, of course, and it's going to be a little bit more involved since we have quotient and then we have to plug and actually get the real value. So let's check this with an example here. We have the function f of x equals x squared plus 1 divided by x squared minus 4. So if we put that on the board, f of x squared plus 1 over x squared minus 4, and we care about the point 3, comma 2. Notice that when you plug in 3, you get a 9 on top, plus 1 is 10, 9 in here, minus 4 is 5, so 10 over 5 is 2. So this is indeed crossing that point. Now we need the derivative, f prime of x, and that's going to be the derivative of x squared plus 1 times times 2x, which is the derivative of x squared minus 4, minus, sorry, went far ahead. Minus x squared plus 1 times the derivative of x squared minus 4 divided x squared minus 4 squared. So now if we take a look at what that is, this is actually 2x x squared minus 4 minus, we're going to get another 2x from here, x squared plus 1 over x squared minus 4 squared. So this actually allows me to simplify really quick. This is going to be 2x factor x squared minus 4 minus x squared plus 1. So I can actually simplify a little bit easier this case. And notice that this x squared minus this x squared is going to go away. And this minus 4 minus minus 1 is just going to give me a minus 5. So from here, I'm going to get minus 10x over x squared minus 4 squared. And that's everything. That's everything in this derivative. So not a bad formula, actually. Now we can plug in 3, and f prime of 3 is going to be minus 10 times 3 over 9 minus 4 squared. And so that means minus 30 over 5 squared, which is 25. And so we can divide by 5 everything. And so this is going to be minus 6 over 5. So with this slope, then we can do what we usually do, and is use the point slope formula for the equation of the line. And we get y minus 2 equals minus 6 over 5, x minus 3. Then after this, we simplify and we obtain the equation of the line, so as usual. So as you can see here now, the equation of the line in this case is going to be minus 6 over 5x plus 28 over 5. And this is the function that is represented. Remember, this is rational function that has issues in 2 and minus 2 in particular. You see here the asymptote in 2 being drawn. And of course, we also have horizontal asymptote in 1, because that's the leading coefficient quotient. All right.